Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. Chapter 15, part 1, randomized complete block design. Okay, so we're at the place where we've first set up blocks of a confounding factor, and then we want to randomize the treatments for each of those individual blocks. But then we might carry out a hypothesis test to test if there's an effect of the treatments under a randomized complete block design. The way we do this is by calculating an F statistic, right? Where the numerator is our sum of squares treatment divided by t minus 1, also known as our mean square due to treatment. And then our denominator is the mean squared error, which is our sum of squares error divided by the t minus 1 times b minus 1, or our mean squared error. So if HO is true, then our test statistic should follow an F distribution, with the degrees of freedom 1 being the numerator degrees of freedom, and the degrees of freedom 2 being the denominator degrees of freedom. We should have a skewed right distribution that peaks at 1. We're going to set up our rejection region and our fail to reject region. The area under the curve of our rejection region is the probability of a type 1 error, or that's set to alpha. Remember, a probability of type 1 error is when we reject HO, when HO is actually true. We can calculate our critical value by finding that alpha level with the appropriate degrees of freedom. And from there, after we calculate our test statistic, we can calculate our p-value. So there's a lot of different ways you can calculate this p-value. One way is by using F tables, and essentially you're going to go to the correct degrees of freedom for the numerator and denominator. You're going to go find your F test statistic, and then you will find the appropriate area under that table. The other way you can do that is by calculating an R. Essentially, the p-value is the probability that your test statistic is greater than that value in the F distribution. So if we find our test statistic to be up here, then really that p-value is this area, right? If our test statistic is back here, then our p-value is the area under the curve larger than our test statistic. Now, to do that in R, what we're going to do, so to find that p-value in R, you can always do PF and put in your test statistic. Degrees of freedom 1 is equal to t minus 1. Degrees of freedom 2 equals t minus 1 times b minus 1. And then the additional thing that you need to put here is lower dot tail equals false, so that it gives you that upper tail probability. All right, here's an example in R where we had 5 treatments with 3 blocks, and let's just pretend that our test statistic was equal to 1. Then right here, the second value of 0.4609, that would be what our p-value would be equal to, because we're doing PF of our test statistic, where degrees of freedom 1 is t minus 1, degrees of freedom 2 is t minus 1 times b minus 1, and the lower tail is equal to false. That gives you the right-hand area. So if I were to draw this out, right, if I was at a test statistic of 1, then this area over here would be my p-value. That would be 0.4609. And the area to the left would be 0.5391. All right. In general, if our p-value is larger than alpha, we're going to fail to reject HO. And if our p-value is smaller than alpha, we should reject HO. So what does this mean in context of the problem? If at least one of the tau i's are different than 0, that means there is an effect of the treatments. At least one of the treatment means is different from the rest. If we fail to reject, then we'd say there's not a significant difference in the treatment means. All right, in the next video, we're going to do an example. So I look forward to seeing you there.